So this is part 2 of solving for polyprotic acids, and we were in the middle of this problem at the end of the last video lesson. So from the first dissociation step, we knew both the hydrogen and the dihydrogen phosphate ion concentration, so you just pull that number into your initial row for this. And initially there was none of the HPO4 minus 2. So let's define our shift in terms of x minus x plus x plus x. Now remember, with these particular calculations, if there's an initial amount present in our row here, we can neglect the x because these are very small amounts that are dissociating. So that allows us to pull down at equilibrium the concentration of H2PO4 minus is 0.19 molar. For hydrogen is 0.19 molar, and then this is equal to x. So let's plug into the law of mass action for this reaction. This will be our Ka2 that we're going to be plugging in for, second dissociation step. Hydrogen ion concentration times the HPO4 minus 2 ion concentration divided by the H2PO4 minus concentration. Now, pulling these numbers in, remember from the beginning we had our Ka2 value was 6.2 times 10 to the negative 8, so I'm going to plug that in. 6.2 times 10 to the negative 8 equals, now plug in your 0.19 for the hydrogen, x for your hydrogen phosphate ion, and then 0.19 for your dihydrogen phosphate ion. Now notice these cancel, and that means that 6.2 times 10 to the negative 8 is actually equal to x, and x, remember, is the HPO4 concentration. HPO4 minus 2 concentration. So now we have found that concentration. So let's come back up here. We're going to substitute that in as we write down our things we were looking for. So now we know HPO4 minus 2, and that is equal to 6.2 times 10 to the negative 8 molar. One last ion to solve for. So we've gotten this one. So now we're looking for the phosphate ion concentration. So that's going to involve the third dissociation step and the Ka3. So this is a very involved calculation, as you see here. All right, so to find the phosphate ion concentration, you're going to do your third dissociation step. So HPO4 minus 2 in equilibrium with H plus, pull off the third proton, and then PO4 minus 3 remains. So let's ice this problem. From this part here, we know that the HPO4 minus 2 concentration is 6.2 times 10 to the negative 8. Remember, from the first dissociation step, we know the hydrogen ion concentration is 0.19, and this would be none initially. Once the equilibrium is allowed to establish, minus x, plus x, and plus x. Again, we can neglect the x here and here, and the reason is because we have an initial amount present, and these are extremely weak acids, so the amount of dissociation is going to be negligible, less than 5%, so we can ignore it. So that means at equilibrium, the concentration of HPO4 minus 2 is going to be 6.2 times 10 to the negative 8. For hydrogen ion, 0.19, and for the phosphate ion, x. Now we're going to be using our Ka3 value for this. This is the third dissociation step. So for the Ka3 value, and that was given at the beginning of the problem, we had 4.8 times 10 to the negative 13. It's extremely small. So that equals 0.19 times x, which is your phosphate ion, what you're looking for, over 6.2 times 10 to the negative 2. We're going to cross multiply here, and then we need to divide by 0.19. So I'm kind of running low on space, so I'm going to just again repeat what we're going to do mathematically. Multiply here, cross multiply, and then divide by 0.19 to get your x isolated. So for the phosphate ion concentration, when you do that, you should get 1.6 times 10 to the negative 19 molar, and that is the final concentration that we were looking for. Now, we also talked about sulfuric acid. I told you sulfuric acid is unique. It's a strong acid. It's the only strong acid that's polyprotic. I said if the concentration is 1.0 molar or greater, you can ignore the second dissociation step. So you're going to treat this just like a regular strong acid calculation. So we're going to assume that's 100% dissociation. You pull off the hydrogen and you leave behind HSO4 minus. Now, if this had been less than 1.1 molar, you'd have to do the second dissociation step similar to what we just did in the last example. So, but since this is 1 molar, we do not have to do that. We just treat it as a regular strong acid problem. We assume 100% dissociation. So initially, we have 1.0 molar, 0, and 0. Minus 1.0, plus 1.0, plus 1.0. So this is all gone, we assume. So this is going to be 1.0 for the hydrogen ion concentration and 1.0 for the hydrogen sulfate concentration. Now it wants the pH, so what we need is the hydrogen ion concentration. So since we know the hydrogen ion concentration is 1.0 molar, we take the negative log of that, and so that's going to give you for your pH 0.00. That concludes the lesson on polyprotic acids.